I just noticed the minor thing.
Sorry?
I mean, I noticed the minor thing. You can see my screen, right? So
Uh,
I think this abstract is for the last talk.
okay, okay.
Yeah, that is a minor thing.
Okay. Yeah. And also I think mm, the date is wrong. It should be August 1.
Yes, yes. Yes.
But today, I think in the announcement today it was correct, right?
Yes.
Okay.
Yeah.
Yes. Okay. Okay. So maybe we can begin now. Welcome everybody to this week's Majorana-Raychaudhuri seminar series. Today's speaker is Wen-Yuan Ai from HEP Institute in Vienna, and he's going to talk about primordial black hole formation from an aborted phase transition.
Yeah. Okay. So it's my great pleasure to talk about my work here. And first, I would like to thank the organizers and especially Anish for inviting me to give a talk here. Maybe I can put it. Yes. So I will talk about the primordial black hole formation from a very special phase, first order phase transitions. And during my talk, please feel free to ask any questions because it is probably easy to understand the details if you ask questions whenever you have a confusion. And here you see that I emphasize on aborted phase transitions. So this is a very special phase transitions, and I will explain how we can have an aborted phase transitions. The talk is based on the work with done with Lucien Hortier from King's College London and also Tevin Zhong from IBS. And my work is supported by European Research Council. Now, so I will start with some motivations about the primordial black holes. And the first motivation is, of course, primordial black holes could be a dark matter candidate. And so we have a lot of evidence that the dark matter must exist, but dark matter still remains mysterious. There are many questions that we do not know an answer. For example, what is the spin of dark matter, and what is dark matter mass? And how dark matter interacts with itself and other standard model particles, and whether dark matter is fundamental or composite, and whether dark matter is microscopic or macroscopic. So the dark matter has a very wide range of masses. It can be as low as 10 to minus 21 electron and as heavy as, let's say, the galaxy mass. So for the mass below 1 eV, then it's called a wave-like dark matter, and this is usually for ultralight dark matter, ultralight scalars like axion or axion-like particles. And between EV and the Planck mass, and it's called particle-like dark matter. And this is the traditional, for example, WIMPs lives in. We can also have dark matter whose mass is larger than Planck mass, but around the solar mass. This is usually the macroscopic objects like boson star, primordial black holes. And this talk is focused on this range of dark matter candidates. So far, we have observed black holes with also a wider range of masses. So we can have black holes from 3 solar mass to 200 solar masses. And this is usually thought as stellar black holes. So these black holes are formed from the death of stellar objects. We can also have black hole masses around ranging from 100 solar mass and 10 to the 5 solar mass, and this is called intermediate mass black holes. And also we can have more massive black holes. It's called supermassive black holes whose mass is larger than 10 to the 5 solar mass. Now the question is, are these black holes can be primordial black holes? Of course, the stellar black holes, by definition, they are black holes formed from stellar evolution, so they cannot be primordial black holes. But for the supermassive black holes and the intermediate black holes, intermediate mass black holes, they could be primordial black holes, or at least primordial black holes could play a role in their formation. For example, you can have some seeds primordial black hole as seeds, and then based on the seed, you can have accretion and so on and so forth, and then finally, you can have a larger and larger black holes, right? So this is also a motivation for primordial black holes. Now, this is additional more information about stellar evolution. And so far, we have observed many black holes. For example, these blue dots are black holes observed by gravitation waves. Okay, and then you can see there's a range, the range from a large mass length from, let's say, as low as maybe 3 solar mass to 200 solar mass. And we also observe some black holes via electromagnetic signals. So this is a violet dots. And then here, anyways, it's a large range mass. But for the stellar black holes, we have two mass gaps. Those are called the lower band mass gap is from roughly 2.5 solar mass to 5 solar mass. This is basically a gap between the heaviest neutron star and the lightest massive the lightest black holes. We also have an upper mass gap. This is basically due to the pair instability in the supernova. So if a supernova is like roughly heavier than maybe around 65 solar mass, something like it, then the temperature would be so high to initiate the pair instability, and so the photons can annihilate to electrons and the positrons, and this will reduce the radiation. So, and this will lead to the collapse of the supernova, and then finally ignite the oxygen burning. And so as a result, you cannot have black hole masses around 50 solar mass and 100 between 50 solar mass and 120 solar mass. Nonetheless, we still observe black holes in this range. So there could be a possibility that these black holes might have a primordial origin. Now, this is another motivation for primordial black holes. So after this introductory motivation, so I will talk about my work on primordial black hole formation. And this is the plan of this talk. So it's okay. So this is a plan of this talk. So I will first give a very brief introduction to the early history of primordial black holes and their standard formation mechanism. And then I will introduce you heating first order phase transition in the early universe. So here heating means that the first order phase transitions occurs as the temperature increases. Okay, so but usually we talk about cooling phase transitions, which happens when the temperature decreases. And then sorry, I can use this one. So and then for heating first order phase transitions, then we can have a very special, a very novel phenomenon where you can see a phase transition can be aborted halfway, and then we can talk about a primordial black hole formation from an aborted heating first order phase transitions. So at last, I will give you a very specific particle physics model realizing this mechanism. So, primordial black holes was proposed for the first time by Ziyadovich and Novikov in 1967, and also independently by Stephen Hawking in 1971. And then in 1974, Bernard Carr and Stephen Hawking gave an in-depth study on primordial black holes, and soon it was realized by George Chaplin and also Peter Matsalos that the primordial black holes could be a dark matter. So this is the standard mechanism of primordial black holes. It's based on the story on inflation. And so for inflation, so we know that at the very early universe, the universe started with a very small size, almost zero size. And there's a very fast expansion stage. And then during this period, then the physical scales stretch. But however, the Hubble radius fixed. The Hubble radius is given by the Hubble parameter, And in this case, you can imagine that there's some vacuum energy dominating the universe, and then this with an exponential expansion of the universe. You can also think about this stage in terms of co-moving scales. The co-moving scales is given by the physical scale divided by the cosmological scale factor. And then thinking about let's say the co-moving Hubble scale is really the 1 over A over H, A times H, right? So the H is constant, almost constant. And then because there's a factor A here, then the co-moving scale decreases, the horizon decreases. So during the expansion of the universe, at each time, you can have fluctuations, right? So fluctuations, because the stretch of these scales, these fluctuations can be stretched out outside of the horizon. So in this picture, you can see that this is the blue lines is fluctuations for a given scale, the co-moving scale, and then since the horizon, in terms of co-moving scales, the horizon decreases. So you can see that how a scale, how fluctuations corresponding to a particular scale will first exceed the horizon. So after the exceed the horizon, these fluctuations becomes frozen. And this also called quantum to classical transition. And later, at the end of the inflation, the horizon, the co-moving horizon will stop decreasing, and then finally you will enter into the radiation-dominated universe, and then the co-moving horizon will increase again. So at some point, this scale will enter the horizon again. And after entering the horizon, then these fluctuations becomes dynamic. So they will lead to, for example, the largest scale formation of the universe. So this is basically how how quantum cosmological perturbations were generated first during inflation and enter the horizon after the inflation and finally lead to dynamic effects. So you can have many lines here, so in different scales. So this is not just, for example, the blue line, it corresponds to a particular scale, for example, the same scale. Okay. And then the standard story about a PBH formation is basically that you can have very large density perturbations generated from the inflation, and later time this density fluctuations will collapse into black holes. Now this is some more details about how these perturbations are generated. So we have a scalar field with and to place the role of inflaton. And at some point, the inflation starts with some point here, for example, the field will slowly rolls down. And as I said, at each point, you can have quantum fluctuations. And the quantum fluctuations exceed the horizon and they become frozen. So this is the scale. And the fluctuations generated at this time has a scale, very largest scale observed today. And so this is called CMB scale. And still later, it will at some point the slow roll parameter will become order 1, and then this is which marks the end of the inflation. So after that, then the field will oscillating around the minimum and give us the reheating. Okay, so the curvature perturbations is simply given by this formula, and H is Hubble parameter. The star means the horizon crossing. So this means that you should enforce the A K equal to A times H. So K is co-moving momentum. Okay, so H is, for example, the H star equal to K over A. Okay, and the epsilon is the first slow roll parameter. And also you should evaluate the slow roll parameter at the horizon crossing at some particular position. Okay. So we have observed the CMB, and then this forces and we know that the curvature perturbation around the CMB scale is roughly 10 to the minus 9. This is very, very small. To have PBH formation, we require the curvature perturbation to be order 0.01 and at some smaller scale. But this cannot be realized from the standard slow roll inflation. It can be seen as follows. So you can see that if you want to have a large p zeta for small scales, it means that a larger k. So you look at a larger k. The larger k means that the fluctuations are generated later time. Okay, so at some point here, for example. So at some point here, and then you can say the Hubble parameter actually decreases, right? So because Hubble parameter is related to the vector energy of the inflaton field, and then the vector energy is lower here, so this Hubble parameter is smaller. While the slow roll parameter, which can be roughly thought about as the speed of the velocity of the inflation field, it increases. So becomes larger. So as a total effect, this p zeta actually decreases. So it becomes smaller and smaller at a later time. Also means that it becomes smaller, smaller for larger and larger k. Okay. So we cannot obtain a large curvature fluctuations from this standard picture. So what we can do, we should add some very particular stage between the CMP scale and also the end of the inflation. And this is usually done by inserting an ultra slow roll phase here. And by doing this, you can see that the curvature fluctuations, it initially decreases, increases from 10 to the minus 9 curvature fluctuations, and once the inflation enter into the ultra slow roll, then there's a strong enhancement of the curvature fluctuations. And then for certain models, you can reach order 0.01 for the curvature fluctuations. And this is how a primordial black hole can be formed at a smaller scale. Okay. Now, there are a lot of discussions on the self-consistency of this mechanism. In particular, the Cristiano and the Yokoyama, they point out that the one loop corrections from the smaller scale curvature perturbations to the larger scale curvature perturbations can be too large, and to spoil the, let's say, the CMP observation constraint. So I'm not familiar with the conclusive statement about the debate. I just want to mention that there's a debate out there. So we should be open-minded about other PBH formation mechanisms. So is there any questions so far? If not, then let's
no,
go on.
But just a comment. So that debate has been resolved. So the corrections are not small. It was just a matter of considering the boundary terms properly and considering the gauge choice properly.
So you think that there's no issue with this mechanism?
There is no issue. I can send you the references after the talk or something if you're interested.
Yeah, sure. So I noticed there's a few papers from this year talking about discussing about the boundary returns, but yeah, thanks for pointing that out. Okay, and essentially there's also another mechanism called the delayed force back decay. This is, in principle, this is not new mechanism. It can be traced back to 1980s by a bunch of Japanese people, but it has been proposed that essentially in a new form and like in 2021 also, and then it becomes kind of popular in the past a few years. And so I will explain to you what is this mechanism. So you start with some scalar field with let's say two minima, and the higher minima is not stable. It's a stable classically, but it is not stable quantum mechanically or on the thermal fluctuations. Okay, so you have a force vacuum and a true vacuum, and if your field is located at the force vacuum initially, then it will decay to the true vacuum via a first order phase transitions. So during this process, for every decay process, you can have a bubble nucleation. So a nucleation of a critical bubble. So after the nucleation, this bubble will grow and collide with each other, right? So and then finally, all the space will be filled in the new phase, the true vacuum, and this is how a first order phase transition complete. Now, how this process can lead to a primordial black hole? Well, so you can, since the bubble nucleation is totally stochastic, you have some probability, and it can happen at anywhere in a stochastic way. So there's a small chance that at a certain time within a Hubble patch, you do not have any bubble nucleation, right? But still you have bubble nucleation already outside of this Hubble patch. The chance is very low, but this is possible, right? But for PBH formation, we do not need a very high chance because the PBH abundance is also very, very small. So this is called as a patch, a delayed patch, okay, for the vacuole decay, and these bubbles will grow, and finally the cloud discharge, and finally the gray region is vacuum energy dominated, and then this is the dark region is kind of new phase, and it describes radiation dominated, because in the end this bubble was very close with each other, and bubble wall also are described by radiation kind of. So you see that in this region, inside of the Hubble patch and outside the Hubble patch, roughly the equation of state of the energy density is different. This is vacuum energy dominated, and this is radiation dominated. So they have different redshift. And because of the mismatch of the redshift between these two regions, the energy density initially the energy density inside of this Hubble patch and outside Hubble patch is roughly the same, but after some time, the energy density here decreases as a to the minus 4, and this is does not change basically. And so after some time, then you can have more energy inside of this delayed phosphovacuole decay region, and this is how you can create an overdensity in this Hubble patch. And if the overdensity is large enough, then this region can collapse into primordial black holes. Okay, so this is also very interesting mechanism, and however, there's still some problem with this mechanism. Actually, this is a very new paper, so come out in this year, and these authors point out that previous studies significantly overestimate the PBH abundance, and then putting this mechanism in question again. So this is why this is basically the motivation why I introduce you a new mechanism on PBH formation. And so we will start with the heating first order phase transitions. So as I said, heating first order phase transitions is phase transitions as the temperature increases. And we know that the first order phase transitions are very common in daily life. So for example, when you cook your lunch, and then you can see bubble nucleations in the boiled water. Okay, this is a typical heating first order phase transitions. And you can also have first order phase transition as the temperature decreases, and this is basically the water to ice transition. But basically the heating phase transitions, I feel that it is more common in daily life. However, one funny thing is that in cosmology, people really do not talk about heating phase transitions. People always talk about cooling phase transitions. And this is a few examples of possible first order phase transitions in the early universe. So every phase transition basically is associated with a certain symmetry breaking or restoring. And here, so we know that in the standard model, we have two phase transitions, Bach hadron phase transitions, and also electric phase transitions. If we believe God theory, then you can also have the grand unification phase transitions. In the standard model, the Bach hadron phase transition and the electric phase transitions are crossover. They are not first order phase transitions. But we can easily make them first order by adding some new physics. For example, for the electric phase transitions, we can add one standard model singlet to make the phase transition to first order. For the quark hadron phase transitions, we even do not need to add new fields. We can make the phase transition to be first order by having a finite chemical potential. Okay. And then this and so somehow so it's very promising to have a first order phase transition in the early models. Now the question is that can we have heating first order phase transitions in the early models? The answer is yes. Now the reason we cannot see this heating phase transitions in this picture is that this picture misses inflation and reheating. So this is a cartoon for the reheating. So it's lovely, like if we put our universe on fire and see how bubble nucleations in this boiled universe. Okay. Now, so I already talked about phase transition with a fixed potential. So you have a two minimal, and then you can have a transition from the first vacuum to true vacuum. But the phase transition in the universe occurs dynamically. You do not have a fixed potential. You actually have evolving potential at a different time, different temperatures. So this is an example. So from above to bottom, the temperature decreases. So at very high temperatures above T1, then your potential looks like this, and then there's only one minimum. So this is not minimal anymore. So there's only one minimum, and so this is a unique phase, unique vacuum. So your field must be located at this point. Now, as the temperature decreases, then the potential start developing a new minima, which is the first vacuum initially, and then but because your field is located at this point, then there's nothing that can happen, right? But at the critical temperature, then when the energy density, the potential energy between these two phases becomes degenerate, and for the temperature even lower, then there's a particular thing happens. So the lower between two vacuum and the first vacuum exchanges. Okay, so the first vacuum becomes a true vacuum here. So the field now becomes metastable, and it can decay to the true vacuum via first order phase transition. This is how a Fourier phase transition happens. Okay, this is from this transition from the symmetric phase to the broken phase. Now we can reverse the story. We start with a temperature very low, below T2, so almost zero temperature. And in this case, this is a unique phase, and your field must be located at this point. And as the temperature increases, and now the phase transition happens between the TC and the T1. So it's different. This is between T2 and the TC. So at this point, then initially the true vacuum becomes a false vacuum, and then you can have a transition from the broken phase to the symmetric phase. This is a heating phase transition. Okay. Now, so in order for this phase transition to happen, we then have a period for the temperature increase, right? And this is a story about reheating. The reheating is after inflation, the field oscillating around the minimum, and you can have it's after inflation, the universe ended up with almost empty and zero temperature. So this is why we must have reheating. Okay. So we will consider, so heating is also a very complicated process, and you can have some non-perturbative phenomena like a premature resonance. But in our work, we follow the perturbative heating, and because in this case, you can have a very precise understanding of this process. You can have an analytic expression for the temperature evolution. So this is a very nice. This is also becomes a classic paper. It has been cited more than 500. So I think this is probably a bit safe to use these analytic expressions. And this is, I show you the evolution of the temperature. So the temperature starts with very low temperature, almost zero, and it grows very fast and reaches maximum. And this is called the maximum temperature. And then later, the temperature will decreases. Now, this is the Tmax. The maximum temperature is still not the reheating temperature. So reheating temperature is defined at the time when the matter energy density and the radiation energy density equals to each other. So this happens at a very late stage. So that's something outside of the plot. So before the reading temperature, say for example here, then all this period is the universe is still matter dominated. So this is very important. Now you see that the temperature increase, the temperature increasing occurs in within a very short period, and you may wonder whether we have enough time to have a phase transition, right? So because this looks too fast. And from this formula, you can estimate the duration. It's like roughly 0.4 half time. And this is actually long enough to allow a first order phase transition to happen, because typical first order phase transitions occurs within like 1,000th of half time. It depends on the parameter beta over h. So for example, beta over h is like 1,000. It means that the phase transition can happen within 1,000th of half time. So it's still much smaller than this 0.4 half time. And actually, in our paper, we will show that indeed the phase transition we are looking at is like 1,000th of half time. So you can have first order phase transitions during this period. Okay. Now this is just to make this picture extremely clear. And you can see at each time, this is still the evolution of the temperature. Okay, at each time, how the potential evolves. We start with very low temperature from here, and so the A is also very small. And then when the temperature increases, the blue dot is a critical temperature, and then your potential takes a shape like this. And now, now when we reach the maximum temperature, then your potential takes this form, and then you can have phase transitions from the broken phase to the symmetric phase. Now in our mechanism, we require the Tmax smaller than T1. So this is kind of a light fine tuning problem, right? So this is like a fine tuning on the heating process. It's not a fine tuning on the theory. The reason is that we do not want the reason that this function is that we want to have an aborted phase transitions. I will explain to you why this is essential. Now, this is a time the bubble nucleation occurs. Okay, so once we have bubble nucleation, we need to look at the bubble expansion after the nucleation. Okay, now this is what happens after nucleation. So at this time, you have bubble nucleation, and you have a critical bubble, right? So inside of the bubble, you are in the symmetric phase, right? So this is the symmetric phase here, and outside of the bubble, you are in the broken phase, right? So the pressure is equal to the negative of the potential. Right, so you see that the symmetric phase has a lower potential, lower potential, right? So inside of the VT0 is smaller, and the outside bubble you have a higher potential. But because this negative sign, so this means that the pressure inside of the bubble is larger than outside. So this means that after nucleation, the bubble will expand. The pressure will push the bubble outwards, and the motion of the bubble will create some friction. Sorry, and then perturb the plasma around the bubble will create some friction to the bubble, and finally you can have some steady state of the bubble. But in the end, the bubble will expand. Okay. Now, a very interesting phenomenon for the heating phase transitions here is that after nucleation, the temperature will decreases because this is the maximum temperature, right? So and then you see that the temperature decreases. So this curve will slightly move around this direction, right? Around this direction. So as long as the temperature lies between Tmax and Tc, the pressure inside of the bubble is larger than outside, and then the bubble is still expand. However, at Tc, the pressures on both faces are degenerate. This also means that the potential is degenerate, and also the pressure are also degenerate. And then for the low temperature, actually the pressures, the real flip side. So the pressure outside of bubble is larger than inside. So this is the picture. So from Tmax to Tc, the bubble will expand, and at Tc, the bubble will stop expanding at that time. For later time, then the bubble will shrink. Right. So this is a very clear picture, right? So if you have questions, please just share with me. So this is, you see that you have first the bubble nucleation, and at some point the bubble shrink, and the bubble will collide at the center and finally disappear. This is why we call it an aborted phase transitions. So the space is never filled with the two regular phase, symmetric phase, because you have bubble and shrink. And now you may wonder, so you could have bubble creations before the bubble shrink, right? And in that case, you can have a complete phase transitions. However, we also require the maximum temperature is smaller than the nucleation temperature, which means that the phase transition rate per Hubble volume is smaller than the Hubble Blankton. And so this means that in each Hubble patch, on average, you have far less than one single bubble. Okay, so this is a very rare process, and then so this means that there's no bubble creations. This is essentially a single bubble dynamics, and then this is indeed can lead to an embody the first order phase transition. Okay. So once we know that there's a PBH, once we know there's an aborted heating phase transitions, and we look at the consequences. Okay. Now this is again the picture again. I repeated the process again and again to make it definitely clear to you. So you have bubble nucleation, and inside of the bubble you are in the symmetry phase, right? So this is the symmetry phase, and outside is you are the broken phase, right? And initially the bubble will expand. Now a very important thing is that inside of the bubble, you actually have additional vacuum energy compared to outside. You see, this is let's take the vacuum energy as a broken phase as zero terminal to be zero. Let's say this is zero. Then inside of bubble you have an additional vacuum energy, right? Outside of the bubble there's no vacuum energy. Okay. So you yes, please. Yes.
I have a quick question about the bubble. So,
Mhm.
are you considering the bubble to be the sub-Hubble horizon? Like after the inflation ends, it would reach the super-Hubble horizon, just like the primordial black hole, some of the perturbations people take. So that's what I was just wondering. Or is it the post-inflation, like after certain E-folding? Like, could you just point out that when it is important?
Yeah, so in this time, the phase transition occurs during the heating. So basically, it's after inflation, but we estimated the bubble size. It can grow. So you see, you have bubble nucleation. Initially, the bubble is very small, right? But after nucleation, the bubble will expand. At some point, this will collapse. So this is the maximal size of the bubble, and we estimated the maximal size. It's roughly Hubble size. It can be it's very difficult to have the bubble size larger than Hubble patch, but it can be very close to the Hubble size, like 0.9, 0.8 the Hubble size. So this is really a very large bubble. And I will tell you that even the bubble does not very larger than Hubble patch, numeric stuff. So later I will show you a paper. So even they can still show that you can have from black holes as long as the bubble size is microscopic, is Hubble size.
So the size is measured after that it crosses the Hubble horizon again, right? I mean, after yeah, like when it freezes, right?
Uh,
So
so,
during the
so
inflation, like we have the first perturbation from super to sub-Hubble horizon, sub to, and then again like the second Hubble horizon crossing. So I'm just interested like at which radius should we consider? Like it is a co-moving, right? So that's what I was just wondering. So
no,
it is the crossing the horizon. I mean the Hubble horizon.
so there's no cross exiting, and there's no horizontal crossing story here. So phase transition occurs after inflation. It's not this is not inflation first phase transition. It's after inflation.
Oh, okay. So you are
Yeah.
not considering that potential to be the inflationary potential. Oh, okay.
Yeah,
Sorry,
yeah, exactly.
Oh, okay. Sorry, I thought that it was inflationary potential. Okay, thank you.
Yes, that's a very good point. Thank you for the question. So here you see that so the point is that inside of the bubble you have additional vacuum energy. You can see from this potential, right? So this is the higher vacuum energy compared to the broken phase, and so this region will grow to a maximum size, which can be Hubble size, and after that this bubble shrink, and finally it will disappear at the center. So you are ending. So you end up with a perturbed region. So although in the end this vacuum energy, the vacuum energy will finally goes to the radiation, because vacuum energy only lives inside of the bubble. But however, there's some time. So there's some time this vacuum energy is stored inside of the vacuum energy. So outside of the bubble and inside of the bubble, there's a transfer between the vacuum energy and the vacuum energy. Radiation energy and the vacuum energy, and vice versa. Okay, so it's really like this is like this region, the bubble inside the bubble is like a bank, and then you have some money. Okay, so you have some money, and then you store your money inside of this bank. Although finally you extract your money back from the bank, right? So it's finally because the bubble will shrink, right? But it's a total effect. And for example, this is the outside of bubble. For example, you imagine this is your neighbor. He or she does not save money into the bank. So they have some money, and then finally he during inflation, economic inflation, then the money becomes less and less, and then here you because you save your money in the bank, then you compensate the inflation, economic inflation. You have more money. So this region roughly inside of this region, you have over density compared to the region that not perturbed by the bubble. So is this clear, right? So if you have any question, please feel free to ask me. So okay, so this is also the reason. Sorry, so this is also the reason the mismatch between the redshift for the vacuum energy and also the radiation, because you have one part of the energy stored in the vacuum, and then you have some part of money that's not redshift, right? Okay, so this is a very nice story. We know that you can have first order phase transition, you can have a perturbed region with overdensity, and then the question is that can we have a primordial black hole from this overdensity region? Okay, overdense region. Now we know that everything, all this story occurs in a matter-dominated universe. As I said before, the reheating temperature, the universe is still matter-dominated. Okay, because this story happens near the maximum temperature, Tmax. And it's very important for the matter-dominated universe. It's very easy to form primordial black holes. So mathematically, you can see that this is a threshold for PBH formation, and this is equation of state. So as the equation of state goes to 0, you can see that basically the threshold also goes to 0. Of course, this also depends on the shape of the perturbed region, and especially it requires the region to be spherical. Otherwise you can have so-called pancake collapse. So this region, if this region is not spherical, it can collapse to a pancake like our galaxy. Okay, so the view are formed to black holes. But for first order phase transitions, the bubble is already very spherical. So this is a very good point for this mechanism, and we expect the PBH formation easily from this overdense region perturbed by the bubble. Sorry. And then this is just a group at King's College London. They actually study PBH formation in a matter-dominated universe with a full numerical relativity. Okay, and then they follow that they consider two different scenarios. In their paper they consider they start with a ring. The ring, this is kind of the density perturbations, and this ring can be larger than Hubble patch. This is visualized Hubble size or smaller Hubble size. So in this picture, I only show the super horizon perturbation, but they also show in their paper the sub horizon perturbations like 1.5 Hubble size can still form two black holes. There are two scenarios. So the first scenario is that this perturbation can collapse into black hole directly. And the second scenario is that this perturbation will first collapse. It collapses to the center, it does not form black hole immediately, but they will create some gravitational well. And this gravitational well will create a surrounding matter because we have a matter, let's say inflaton, right? Oscillating inflaton field, right? So and it creates an inflaton field into this region, and finally it will become black holes. And the PBH mass will grow and from this accretion until radiation domination starts. So this the mass growth will stop at the reheating temperature, and then the PBH mass is evaluated basically as a Hubble mass at the reheating temperature. So this is a formula for that, and you see that this is inversely proportional to reheating temperature. Okay, and then this will give some constraint on the PBH mass for our mechanism. But the message is
we have 5 minutes left.
Okay, so I will be very quick. So this is also, and this is very this is how we can estimate the PBH abundance. So basically, you count how big chance you can have bubble nucleation, right? So this is the bubble nucleation rate and integrated over time. And I will skip this one. So this is also we define some rapidity parameter. It's basically beta over h in the conventional discussion on first order phase transitions. So in the end, we find the PBH abundance is given by this formula, and it's very sensitive to the phase transition rate. Okay, so and also it's sensitive to the reheating temperature, and this is rapidity parameter is take 10 to the 5. Okay, so sorry, so I said this wrong. So this phase transition occurs like into 1/10⁵ Hubble time. So even much faster than I told. So it can happen within, let's say, the heating the shorter region between 0 temperature and Tmax, roughly. So finally, we show the constraint from our the PBH from our mechanism, and we have two parameters. The one is the decay rate, the phase transition rate for Hubble volume, and also this is PBH mass. The PBH mass is, as I said, is related to the heating temperature. So this is basically the parameter of the heating temperature, and you can see that indeed you can have PBH abundance like roughly one in this narrow window, and also you see that there's a few brown bonds. And for this dashed line is a line below on the left of this line is black hole is too small and it has evaporated very fast. And our PBH has also a large upper bound on the mass. This is basically due to the lowest latent temperature. So as I said, the PBH mass is inversely proportional to the latent temperature, right? So if you want to make the PBH mass larger and larger, you have to make the latent temperature smaller and smaller. And then the latent temperature cannot be smaller than the BBN scale, roughly 5 MeV or 5 MeV. Okay, so this is at upper bound. I will probably skip the specific models, but in any way, so we consider a classical scale in the scalar model, and we show that you can have a first order phase transitions and means a very large rapidity parameter. So beta is basically beta. So this is you can see that beta is roughly 10⁵, and also we also computed the decay rate. Okay. Yeah, I think I do not have time to go to details of this model, but this is also a very similar model has been used by many people on PBH formation from the delayed phosphatic decay. So I also want to mention that this mechanism, this PBH formation mechanism, does not rely on heating. You can also have an inverse phase transitions. Inverse phase transition without heating. So this is an example. So from this paper, so I didn't. So sorry, so I forgot to cite this paper. This is a paper published in like 2018, and this is have a very interesting evolution. You have you first start with a potential like this, and finally you develop some minimal, and this is a crossover, and then after some time this minimal will uplift again, and then you can have phase transition from the broken phase to the smooth phase, and after that the phase will decrease again. So you have a three-step phase transitions. First phase transition is crossover, and the second phase transition is can be first order, and finally you can again have first order phase transition from the smooth phase to broken phase. So we are looking at whether we can have PBH formation in this model, and even without reheating. So if this is possible, this is very interesting because reheating, the heating is very complicated. Right? So any non-perturbative phenomenon probably can spoil our simple pixel. Now, this is a summary of this talk. So there could be heating first order phase transitions, and which could be aborted. So this will give us a very simple dynamics. Think about our evolution. So I want to mention that the first order phase transitions, heating first order phase transitions, have not attracted much attention. So it was proposed only very recently, like in 2023 or so, and so I believe that there's much more phenomena can be studied on heating first order phase transitions. So for example, you can have inverse electric phase transitions. This must happen, right? So but the problem is that the gravitational signals could be low because you have heating and then gravitational waves can be diluted. But still, I encourage you to look into possible phenomenology based on heating first order phase transitions. And the second point is that this period bubbles can generate spherical energy over density in a matter-dominated universe causing PBH formation. And finally, the PBH, so the third part is the PBH mass only depends on the reheating temperature. And also, we can have a large mass and abundance ranges. And finally, in principle, we can also have inverse phase transitions without reheating. And then it would be interesting to see whether we can have PBH formation without reheating. Finally, thank you very much for your attention.
Okay.